Okay, Sekunde nochmal aus. Sag mal was.
Ich kann viel sagen. Ich bin auf 3 Stunden Vorlesung eingestellt.
Viel sagen. Sehr gut. Geht's schon los? Ja, ich glaube, wir sind live. Alles klar.
Okay, good. Then let's start. Sorry for the delay. So today we talk about hash functions and how we can look at different versions of hash functions as we have seen so far, namely universal one-way hash functions, which we really can prove can be constructed from one-way functions, although I won't give you the proof. But that then finishes, and I'll also state a different version of hash then sign that's tailored towards these universal one-way functions. And then if we combine these things, replace the hash then sign in one-time signatures, the hash functions by universal one-way hash functions, we get one-time signatures for messages of arbitrary length that can be constructed from one-way functions, because we know that one-time signatures can be constructed from one-way functions. Universal one-way hash functions can be constructed from one-way functions. Then we have one-time signatures of arbitrary length. And then we can use our refreshing paradigm and pseudo-random functions to actually construct digital signatures from one-way functions. And then in the second part, we look at constructions of hash functions. Although I will only give you the most important construction of going from hash functions for messages of fixed length to arbitrary length. Constructing hash functions for messages of fixed length is a art, and in particular in practice. So I won't go into this. It really would completely deviate from the rest of the course. So I'll just stick to this important construction of fixed length to arbitrary length. That's called the Merkle-Darmstadt construction. And then we also look at the so-called tree version of it. And that's actually very practical and important for practical reasons. Okay, so what have we done so far? We have seen hash functions in the hash then sign paradigm, although hash functions have many other applications. In fact, they are often called the workhorse of cryptography. There are actually very few applications of crypto that don't use at some point a hash function. So they really show up in a lot of places. The construction of hash functions, as I said, proceeds usually in 2 steps. That's something that we already saw in different contexts as well. We first construct hash functions for messages of fixed length. Then we have techniques to turn that into hash functions for arbitrary messages. The first, as I said, is art combined with science, and that leads to things like SHA-1, SHA-2, SHA-3, and many others. SHA-3 actually is a little bit of an exception because SHA-3 can immediately lead to hash functions that are defined on messages of arbitrary length. And we present 2 important techniques for this step. The chain-based hashing and the tree-based hashing, or so-called hash trees. And we also, as I said, will look at universal one-way hash functions and how they can be used in the hash then sign paradigm. Although we have to modify the hash then sign paradigm a little bit. You see actually why we have to modify it if we want to use that with one-time signatures. Okay, and I first go to this step. So the first part will be to discuss universal one-way hash functions. And you remember our security game for hash functions, the collision finding game. The attacker had to find 2 pre-images that map to the same hash value. In the universal for the universal one-way hash functions, we modify that a little bit. We give the adversary a little bit more power. And that is then defined by the so-called second pre-image finding game. So as before, we have a hash function, which consists, as before, of two algorithms, the key generation algorithm and the hashing algorithm. The key generation algorithm picks a key, and then the hash algorithm give a key, and the message computes the hash, which we usually define as hs of x. S is a key. And remember, the key is not secret in hash functions. It's something that we give to the adversary as well. Right? Everybody has to be able to apply hash functions. So then the universal second pre-image resistance game is defined as follows. The common input is 1 to the n, so n is a security parameter. Now, A, at the very beginning of the game, is allowed to pick an x from 0, 1 star as ever he likes it. So he outputs an x. Then C chooses the key using the key generation algorithm and gives S to A. Okay? And then in this third step, given S, given this X, and remembering all kinds of information that he has used here, A outputs an X prime, also from 0, 1 star. And we say that A has found the second pre-image, and the output of the game is 1, if and only if X prime is not equal to S, but the hash values are the same. Okay? So where do we give A additional power? He outputs this X here in the first step. And then he has to find, or actually, yeah. And then he has to find the second pre-image for that. Actually, it's a little bit less power. Sorry, right? He has to first pick this X. Right? So that already fixes his one of the arguments that he eventually has to output, and then only then does he see the key S. So he has less power. Sorry, I misstated that. Okay, but he's the one that picks this X here himself. So he can argue that for some X's, it may be easier to find the second pre-image than for others, but he has to do that independent of the key. Okay. And then we do the usual things. We write second pre-image A pi n for the output of the game on input 1 to the n, and set this second pre-image advantage as the probability that the second pre-image A pi of n is 1. And we say that the hash function pi, consisting of the two algorithms gen and h, is a universal one-way hash function if for every probabilistic polynomial time algorithm there's a negligible function such that the second pre-image advantage is negligible. There's a negligible function in n. Okay. So one way, why it's called one way, well, actually, given that x, then he has to find a pre-image for this value, a second one. So he has to invert this h of s. Okay. Yep. So it's a little bit, this is if the keygen, if pi is collision resistant, then pi is also a universal one-way hash function. But the converse is not known to, actually, it's probably not true. There are technical details that you have to take into account. Okay. Why is that true? Well, if you are collision resistant, in the collision resistance game, nobody precludes A from picking this A without actually taking account S, right? So this game is covered also by the collision-resistant algorithm. An A that follows these rules can also be applied in the collision resistance game. But here it's more restrictive. Okay. This is this. And as I said, we know how to construct these universal one-way hash functions from one-way functions. Yeah. It's a not so easy construction, but you can do it. Okay? Okay. But because universal one-wayness is not as strong as collision resistance, if we want to use universal one-way hash functions in hash then sign, we have to use a slightly different construction. Okay? They are not quite as powerful, hence we have to modify the construction, be more careful in the hash then sign. Okay? The original hash then sign is just hash the message, sign the hashed message. Okay? If we do this with one-way hash functions, it's a little bit more complicated how we do this hash then sign paradigm. And here is the construction. Okay, so let L be a polynomial, let pi prime consisting of these three algorithms, gen prime, sign prime, verify prime, be a signature scheme with message length L of n plus n. So we can sign messages of length L of n plus n. And I assume that pi h is a hash function, which is a function, actually hash function, which hash length L of n. Okay, this is this L of n, such that keys on input 1 to the n have length exactly n. Okay? So this is a little bit more complicated than in the hash then sign with collision-resistant hash functions, where we just said that the message length, the signature scheme with message length had to be L of n, and the hash length had to be L of n as well. Those two had to fit together. Here we have that the signature schemes must have message length L of n plus n, and we have this additional restriction for the hash function. That it's here exactly n, it's convenience. If you do here some other length, then this becomes this other term. Okay? And now we can define a signature scheme gen sign verify, which is now on messages of arbitrary length. We assume that pi h is a hash function that works on messages of arbitrary length as follows. The key generation algorithm for the new scheme is simply the key generation algorithm of the fixed length signature scheme. The signing is done differently. So on input 1 to the n and secret key sk and message m in 0, 1 star, the signing algorithm first chooses a key with the key generation algorithm of the hash function. And then it signs with the signing algorithm of the pi prime, it signs this key s concatenated with the hash value of m with key s. Okay? And outputs as the signature s and sigma prime. Sigma prime being here the signature here. Okay? And the verification, once you get the public key, a message, and signature pair m sigma. Sigma consists of s and s prime, and sigma prime, where s is such a key. We output one if and only a verification of the original scheme on s concatenated hs of n, and sigma prime is 1. Okay? Yeah? So if you compare this to the original hash then sign, in the original hash then sign, the key generation consisted of running the key generation of the original scheme and picking one key for the hash function, one global key for the hash function. Okay? Whereas here, what we do, the key is just the key from here, but for each signature, we compute a fresh hash key and sign that hash key in our signature as well. So it should remind you a little bit of a refreshing paradigm. So for each signature, a fresh hash key. And then we sign the hash value as before, but concatenated with the key itself. Okay. Obviously, we could have done this construction as well with collision-resistant hash functions, but it would be wasteful. Because if we have a collision-resistant hash function, we can pick a general global hash key. If it's only a universal one-way hash functions, we cannot do that. But what we can prove then, we can even show that if pi prime is a secure one-time signature and pi h is a universal one-way hash function, then this thing in construction 9.2, this pi in construction 9.2 is actually a secure one-time signature. And I think, yeah, no, okay. Yeah? If it's, yeah, that's what you can do. So if pi h is, if pi is actually, pi prime is a signature, secure signature, then it's also secure signature scheme. But we don't actually need that for our construction then if we look at our sequence of steps to design signature schemes from one-way functions, we would just use this here. Right? So we first there constructed one-time signatures for messages of fixed length. We wanted that to extend to one-time signatures for messages of arbitrary length. Now we can use this construction using universal one-way hash functions, and we are happy. Yeah. The proof of theorem 9.3 is very similar to the proof of the security of hash then sign. You have to modify things a little bit, but not much. In fact, when you go to the scheme, what you will, if you go to the proof, you will also, if you remember hash then sign, in the proof we had the distinction of a forger against a new scheme, namely whether the hash value of the message that it outputs is the same as the hash value of one of the query messages, or whether it's not the case. And here you will actually do something similar, but you also look at the key S. Has the key S been used before? Stuff like that. Yeah? And if that key has been used before, then you will actually be able to find a solution to the second pre-image game. You will be successful in the second pre-image game. So this is really tailored towards this construction or the properties of a universal one-way hash function. Okay. Okay. So that's how we can get around using collision resistance hash functions, which we do not know how to construct using one-way functions, and instead use in our construction of secure signature schemes, use universal one-way hash functions, which we know how to construct from one-way functions. Okay. Yep. Good. Any questions about this? If not, then what I want to do is I want to go from, if I go back here, we want to go to this part here. Okay? This step here. How do we construct from a hash function that is, say, collision resistant? Again, we switch now again to collision resistant, but works only for fixed length messages. How do we go to arbitrary length messages? And the important technique that we see here is the Merkle-Darmgard construction. And I will present this in two different ways, the simplified way and then the not simplified, the full version, although there are many other versions of Merkle-Darmgard that can deal with all kinds of parameter sets. And I'm just doing one of the easier parameter sets. Okay. So here is our goal and the ingredients that we have. So we have L, a polynomial, pi bar consisting of gen bar, h bar, be a hash function for messages of length 2ln, and with hash length L of n. Okay, so it hashes messages of length 2L of n to messages of length L of n. So that's kind of very restrictive, but you can play around with these parameters. In particular, this 2 here is pretty much arbitrary. Like I could do anything, any other parameter there, but the construction would involve other parameters as well, and this is the easiest way. But the basic idea is always the same. Okay, so now we define this new hash function as follows. So the key generation algorithm of the new hash function is simply the key generation algorithm of our original hash function pi bar. Okay? So keys are as in pi bar. Now h on input 1 to the n, key s, and a message x in 0, 1 star. Okay? So it does the following. It sets b to be the length of x divided by L of n, rounded up. Okay? So you partition, if you have an example, so L of n, say, is 4, and I have my x is 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 0. Yeah, okay. And okay. Then I have here that the length of x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? If I okay. So b in this case is 15 divided by 4, rounded up, which is 4. Right? Yeah. So then I pad x with zeros such that the length of the padded bit string x bar is now a multiple of L of n. Okay, so let me deal with 2 zeros, and just let me note I put a bar above the 0 to indicate that it's an extended x bar, right? So this is now x bar. Okay. X is This is X bar without the barred zeros. And then I partition X bar into B blocks of length L of n, X1 through XB. So I partition it now in these 4 blocks. Then I have another block. So this is X1, this is X2, this is X3, this is X4. And then I have 0, Z0, which is a bit string of L of n zeros. So this is 0, 0, 0, 0. Yeah. And now I compute for I from 1 to b, I set Zi to be the value of h bar with key s on Zi minus 1 concatenated with xi. Okay, so x1, Z1 would be sort of these two here, right? So Z1 is h bar of s, and then I take this guy and I take this guy. Huh? Okay. And then I take Z2, I take h bar of s, and I take this one and concatenate with this one. Yeah. And eventually I output the last value ZB. So ZB is h bar of s of ZB minus 1 concatenated with the last block. Okay. But my output is not just ZB. I also include the length of x. So the output would be, in our case, this ZB concatenated with 15, which I obviously write down in binary. So it would be 1, 1, 1, 1. Okay? Because 15 is 8 plus 4 plus 2 plus 1. Right? Okay? Okay? That's it. I won't prove the, actually, I will give you a little different construction later on, because one disadvantage of this thing is, in practice, we want hash functions that have an output of fixed length. Right? Say 256 bits or 512 bits. So this is not good, because the length, the description of the length of x obviously depends on the length of x. So the longer x becomes, the longer the hash value becomes as well. This is usually not what we want. Okay. So we want to get rid of this guy here. We would like to replace this by something else. But before we do that, the question is, why did I include this length of x in this thing? Yeah?
Simply omit some of the blocks and have a collision.
Some of the blocks? No, not really. That probably doesn't work. Blocks, omission of blocks is probably Not good. So eventually we want that if this guy, we want to be able to prove that if this guy is collision resistant, then this new construction is also collision resistant, right? And what I'm saying is that if I do not include this thing or something similar to this, then this is not going to be collision resistant. So if I just do this here, just output the last ZB, that is not collision resistant. And you said omit complete blocks. So just say, do this here. Probably no, that doesn't work. Don't be too greedy. What's the difference in hash value if I do this x or this x where I put in, so I delete this 0, but because I have to fill it up, pad it, I have just 2 zeros. So 14 bits, the last 2 being 0. There will be no difference in the hash value because the algorithm doesn't know whether this is a padded 0 or whether it's a message 0. Right? Okay, so this doesn't work if I don't do that. Okay, it's clear. So then the idea may be, well, why don't I just use a more complicated padding scheme? Well, any padding scheme that you use basically has this problem. Right? So in all these schemes, if you pad, you have to include here some information that tells you how much did you pad, or roughly information on how much you padded. Okay? It need not be exact, as we will see, but you need some information on the length of the original message so that you know, okay, this is that you, not by just padding, you get collisions. Okay? Yeah. But as we'll see, this padding, this extension here is too wasteful. We can do better. Although we need to use sort of an old trick that we used before already, once at least. Okay, so we want to do something better here. Okay, actually the trick is not so deep. Remember, we are dealing with polynomial time adversaries, right? So no adversary can output messages for collisions that are exponentially long. So if I have a scheme that's secure for messages that are somewhat exponentially long, but not arbitrarily long, I'm fine. For the really, really long messages, I don't care because no polynomial time adversary can output it anyway. May seem like cheating a little bit, but actually in practice, you cannot output messages whose length exceeds the number of atoms in the universe. Right? If you make it that long, then you are safe. Okay. So, and that's actually what we do in the real Merkle-Darmstadt. Here's again the construction that I wrote down there. Here is how we do this, how we get around this problem of having a variable hash length. The setup is as before, and as before I can modify this in all kinds of ways, doesn't matter. And now we have this construction 9.5. On input 1 to the n, we choose again the key using the original key generation function. And then we say that h on input 1 to the n, key s, and a message x in 0, 1 star, whose length is upper bounded by 2 to the L of n. And I don't care what you do for longer messages, because no adversary is say that the hash value is, I don't know, L of n zeros. I don't care. No adversary can output such a message. And in practice, no such message exists. Yeah? Okay, and then I do the following. I said B as before, except that now, because I know that X is capital L, I redefine this. Again, I pad X with zeros such that the length of the padded bit string X bar is a multiple of L of n. And then what I do is I set X bar to be X1, XB plus XB as before. And I define a next block, a B plus first block, which is the representation of L, of capital L, with exactly L of n bits, little L of n many bits. Because capital L is strictly less than 2 to the L of n, the bit representation requires at most L of n many bits, and I use leading zeros to fill it up. Okay? In this case here, if I would do this here, L of n and the length of the binary representation of capital L really uses exactly 4 bits, so there is no need to fill it up with leading zeros. Then I pick Z0 as before. And now I do the same trick as before with the ZIs, except that I now have also a B plus first block. And I just run this to the very end of B plus first, and the last thing is just ZB plus 1. Okay. So it's basically the same thing as before, except that I restrict myself to messages of really long but upper bounded length. And then I include this here, the number of the length again filled up with leading zeros, and that's it. Yeah. Yeah. So the construction is very similar, except that you have a B plus first block here that is appropriately defined. Yeah. And what we want to show is that if pi bar is collision resistant, then either of these constructions is collision resistant. And I will only prove it for construction 9.5. The other construction is even a little bit easier to prove. Okay? So, proof (9.6) for construction 9.5. So formally, what I have to do is, again, given an arbitrary adversary against the collision resistance of pi, I have to design adversary against the collision resistance of pi bar. I won't do that today. I will just show you how, given a collision in pi, you can actually construct a collision in pi bar. And then you would have to transform that into an actual adversary. But that's really just, it's very simple. Okay? So just show how to get a collision in pi bar from a collision in pi. And you will see that the way I get from one to the other is easily doable in polynomial time. Okay? So assume x prime are such that x is not equal to x prime, but hs of x is equal to hs of x prime for some key, for key s. This works for any key, so I don't have to specify that it's generated by the key generation algorithm or whatever it is. Okay? So now we distinguish two cases. And as you can expect from what we mentioned when we talked about this thing here, we distinguish whether they have the same length or not. Okay. That obviously is a good candidate to distinguish things, right? So we have A, x is not equal to x prime. And the second case is obviously x is equal to x prime. Good. So let's first do case A. This is the somewhat easier case. So we have L, say, is the length of x. L prime is the length of x prime. We know that L by assumption is not equal to L prime. And then but we know that both our L and L prime are less than 2 to the L of n. Okay, that's a legitimate collision. And then we set B to be L divided by L of n. We have some security parameter in mind. And we have B prime, which is L prime divided by L of n. Okay. B and B prime may or may not be different. Okay, because of the rounding up, they can be the same, although L is not equal to L prime, but we won't use that. Okay, but what we know is when we can then partition x into x1 up to xb, and x prime we can partition into x1 prime up to x prime b prime. Yeah. And we define z and z prime as in the algorithm, except the primes now refer to the input x prime. Yeah? So that I prime defined as in construction 9.5 for x and x prime. Okay. Good. Let me just this way here. So this looks a little bit like in a horror movie, right? But anyway. So by assumption, we have that ZB plus 1, which is h of s of x, which is h of s of x prime, which is z prime b prime plus 1. Right? The values are the same. The number of blocks may be different, but anyway. Okay? However, this we know is h bar of ZB concatenated with the last block, with this length of this thing, right? So this is xb plus 1, and this guy here is h bar of s of z prime b prime concatenated x prime b prime plus 1. However, we know that xb plus 1 is not equal to x prime b prime plus 1. This is L prime and this is L. They are not the same. Even if I do leading zeros, I mean, already without the leading zeros, they stop with a 1, and then there's leading zeros. You cannot make those two things by leading real zeros the same. That doesn't work. But that implies that this here, this and this is a collision. Right? Because these two blocks, the last two blocks, already are different. So they are these blocks, these two arguments are different because the last blocks are different, but they have the same value, hash value, so this is a collision. And we are done. Yeah. Okay. So leading zeros to a number, binary representation of a number, that is not so harmful than just padding with zeros, because you know that there is a 1, and then there are just zeros. Okay, so that's the first case, case A. Yeah? If the length is different, and in such a collision for pi, we are done. So in this case, this argument obviously does not apply. Yeah? But in this case, we know that these two values here are the same. So the number of blocks is identical in case B. Okay? And that is the property that we are going to exploit there. This may or may not be the case here, but that is not relevant. But here, in case B, we will exploit that property. Can I erase everything? Actually, I keep this notation here with L prime, B prime, and B. But now I know that B prime is B in this case. Okay, so let's do that. So case B. And now we have B is equal, so L is equal to L prime, and B is equal to B prime. So, okay, we have x is equal to x1 up to xb, and x prime is equal to x1 prime up to xb prime. So no need to prime the b because they are the same. Okay? And these are the unpadded things. Sorry, they are the padded things already, but they do have the same length. Okay? So since x is not equal to x prime, we know that there exists an I such that xi is not equal to xi prime. Okay? The padding cannot destroy this, that there must be a block, because they have the same length. So I append the same number of zeros to both of them. So I pad the same number of zeros. If then all blocks are the same, the padded number of zeros is the same, then the two strings have to be the same, which they are not by assumption. Yeah? So there is a block where it's not the same, and then define k, the maximum over all k, such that z k minus 1 concatenated xk is not equal to z prime k minus 1 concatenated x prime k. Okay. Did I do this correctly? Yes. Let me do this. Not to confuse you too much. Let me just switch this to this J. Okay. So the longest, or the largest index for which these two blocks are not identical. Okay. So k is well defined. This implies k is well defined. Meaning there is an index, at least one index for which this is true. And that follows because there is an index where these two are different. No? And when these two blocks are different for the corresponding zi minus 1, these two are also different. But there could be something further on that although these two are the same, these could be different. Right? We don't know. So the difference in these concatenated blocks could also be due to the difference in the first part. Yeah? And that's why we do yet another case distinction. So again, two cases. The first case is that k is equal to b plus 1. And the second case being k is strictly less than b plus 1. Okay? Huh? So case 1. Case 1 is very similar to what we've done before in case A. Because then if k be plus 1, we know that, so then z b concatenated x b plus 1 is not equal to z prime b concatenated x prime b plus 1. That's case 1. But because we assume that the collision, but we have that h bar of s, we have a collision in between x and x prime of z b concatenated x b plus 1 is equal to h bar of s z prime b concatenated x prime b plus 1. Well, because this is the last hash value, the last value, that's the hash value for x and x prime. Again, the two things, so this is a collision in pi bar. Yeah?
Why do we get the max of days? Because if we have one index where this is different, these two parts, the z's after that index is are always different, right?
No, after that they are the same. The reason why I pick this k will become clear in case 2.
Okay.
I want that beyond that, these two are the same. In particular, these two must be the same.
Okay.
But before they were different. Something was different. Okay? So it's the last one. So I know that at that point they are still different at k, but at k plus 1 they are the same because k is the maximum. And that will lead to a collision. Okay? I really want that. But and that's why I had to do this case distinction. For b plus 1, there is no next index. Where now, if it's b minus 1, I know there is a next block of concatenated things. Right? And I can use that.
So basically, we assume if before some xj and x prime j are different, at some point the resulting hash would be equal.
That's
even if we have some different.
Yeah, and I need the last one, as you will see.
Okay. Yeah,
I really need that.
Okay. Yeah.
But this will become clear when I discuss the last case. You will see that this really is where I need that. Okay. Oops. So now let's collect all the information that we have. So case 2, k is strictly less than b plus 1, which implies that the k plus first block still exists. So, yeah. Right? So what do we know? So we know by definition zk minus 1 concatenated x, k is not equal to z prime k minus 1 concatenated x prime k. And because k is maximal with this property, we know that zk concatenated xk plus 1 is equal to zk prime concatenated x prime k plus 1. Right? And this block exists because k is less than b plus 1. It does not exist in this case, and that's why we do the case distinction. Well, and now you know what we do, because zk is h bar of s of this value, right? And this is the same as h bar of s of this value, which is zk prime. And this I can, well, if these are the same, then all the individual blocks must be identical, right? And this implies that this now is a collision. So these two things here now are a collision. So zk minus 1 concatenate xk, z prime k minus 1, xk prime collision in pi bar. Right? And that's it. So now you see why I use the maximum, because I want that. Okay. And that finishes the proof. You can easily see that the case distinction as an algorithm, yeah, you check for the conditions, and then given the conditions are easy to check, and then given the conditions, you know what you have to do. Compute the k, the maximum, yeah, compute all these things, compute all the individual blocks, z, and so on, and you're done. Okay. Yep. So in this case here, like the case B is you have the same number of blocks, and then you go in parallel. Last block, compare, next to last block, compare, next to last block, compare. And you know, since you have the same number of blocks, you can really do that, which you cannot do in the first case. There's something has to happen in the last block, the individual last blocks. Okay. So that is the Merkle-Darmstadt construction. I want to present a slightly more efficient version of it, where if you see this here, right, it's a list. Well, as a computer scientist, you say if there is a list, there should be somewhere also a tree construction. Right? It's the same thing that we did in the refreshing paradigm. We had this with chains, and we had this with trees. And now I do the same thing here. It's very similar construction. And I don't want to bore you with the indices. I'll just show you the picture. How you compute a hash function. Right? Basically, you do the same thing as before. So you have these blocks. You have included something. You have padded with zeros. And again, you can do both versions here. You can either do this version here where you just include as the last block the length, or you are slightly more clever and include the length, but you restrict the length of the messages and pad with leading zeros. Yeah. So, and then you have such, in our case here, b plus 1 is 8. Right? And then what you do, so these are the blocks, and you have the h bar. And now what you do is you compute in a tree-like fashion. You compute the hash values of these two, hash value of these two, the hash value of these two, hash value of these two. Then you combine the hash values here, hash and hash. Again, we have 2ln to ln, right? So everything works out. Then these hash values, and you combine these hash values, and eventually you come to the root, and that's the hash value of these two things, and that's your output. That's the overall hash value. If you are interested in the technical details, this is it. The numbers are a little bit, this t is a little bit differently defined because why is it a little bit differently defined? I need the number of blocks to be a power of 2, right? That's all I do. And because otherwise I want a complete binary tree. Well, what I do is I pad with zeros until I get a complete binary tree power of 2 as the number of leaves. But then everything is as before. And what one can show is that if pi bar is collision resistant, then this new construction is also collision resistant. Yeah. Yeah. Okay. So if you look at this construction, this has many advantages compared to the previous construction. There is one disadvantage that it has, which relates, you have to pad a lot more, right? Because padding it such that the length becomes a power of 2, that may almost double the length of the message. So you really include a lot of stuff that's not necessarily in there, right? The next power of 2 after 17 is 32, right? So you almost double it. But anyway. But then, now assume you're only interested in the application of hashing as data integrity. So what you do is you store your data with a cloud provider, which you do not trust. He may give you wrong answers if you ask for the data back. So what you do is, before you actually store the data with the cloud provider, you take the hash. Okay? You compute this hash function here. Yeah? And now you do not want to retrieve your complete data. Right? You only want to retrieve parts of your data. That's why you stored it probably by a cloud source provider anyway. Right? So you only want to have, say, 1 block. Okay? If you use this construction here to check for this, that no block has been modified, you need the complete chain. All of it. Okay? However, if you want to check, for example, if x3 is returned correctly, the source provider, the cloud provider, just said, okay, here's x3 and x4, and here's the hash value. And by the way, this is the hash value also from the first 2 blocks, which I don't give you, but this is the hash value. And then I give you this hash value and this hash value, and I give you eventually, and this is the things that you get. And then what you do to check, okay, this is the value that you stored locally. You got from the source provider, from the cloud provider, these 2 values. So you check that the hash value of these 2 is this here. Then you check that the hash value of this is this and this. This is the hash value of these 2. And then you check these 2. Then you check that the hash value is here. Okay? And what you can argue by looking at it, that if he wants to give you a wrong element here, he has to find a collision somewhere along this path with the descendants. Yeah? It's not so difficult to prove this. Look at a few cases, and then you'll manage to find that. Similarly, if you want to modify data, so you have stored this data in the cloud, and I say, oh, I want to change this value here. I don't want to change the whole thing. I just want to change this value here. So I send it over there and do the whole thing. So then what I have to do, obviously, I have to change now the hash value here at the root. But I can do that by just getting from the cloud provider these values here. You do check X3. So you then give me the new one here, the old one here, new one here, old one here, and then I recompute my hash value. And again, if it does something funny, I will detect it. Okay, so you can really sort of read and also write. If you want to do that here, in this construction, you have to change everything. Right? Because everything depends on everything else. So this here is a real nice data structure that provides integrity. So, and this is like the easiest, one of the easiest cases of so-called authenticated data structures, where you outsource data and then you can check that the integrity of the data is given. So you see again, so this is, and you should also see that this is very similar to, as I said, the tree construction in the refreshing with digital signatures. So this is really a really important construction, independent of this application in going from fixed length hash functions to arbitrary length hash functions. Yeah. Okay, now let's do a short break until 9:50. And after the break, I will talk a little bit on, about attacks on hash functions. And we'll talk about the so-called birthday attack on hash functions, which explains parameter choices in practice. Okay, so let's do this 13 minutes break. Okay.